Okay, so here we come to the ambiguous case of the sine rule. Now, we don't need to worry about this about cosine or tangent. It's only with the sine rule. And when we get to unit circle, you'll start to understand a bit more about why this is so. There's a YouTube video there that you can watch about it. But with the ambiguous case, so ambiguous is when there's more than one interpretation about what is going on. And this is what we're talking about here with the ambiguous case of the sine rule. So this is what can happen if we have a triangle where we know two sides and an angle that is not the angle between the sides. In this scenario, the angle we are trying to find can be obtuse or acute. Okay, we don't actually know the size of that angle that we are trying to find. So when using the inverse sine function on your calculator, this calculator will give only the acute angle. It will only give you the acute angle. You can find then the obtuse angle fairly easily, but you've got to be aware of which one you're finding. Just double checking, acute means less than 90 degrees and obtuse means less than 180 but greater than 90 degrees. Okay, now if you're given a diagram, you may be able to tell whether the angle is acute or obtuse, but you don't always get given a diagram, or it might not always be clear. So here's an example that illustrates what I mean. Okay, so the two triangles have two corresponding sides equal. So A and B are of equal length in both triangles. Okay, in this first example, the sine of 110 also equals the sine of 70 degrees. Okay, just want to prove that to you. Okay, so sine 110 degrees, Control Enter, 0.939, 69, yep, sine 70 degrees, Control Enter. They are the same. Okay, so if we're only told the length of A and B, we would not know whether this angle here is the obtuse or the acute. Okay, because they work out to be the same thing. So we don't know. That's why it's the ambiguous case. So there is something to tell you, though I think it might be a little bit ahead of what we're doing here, but I've got these from my further maths notes, that if we are looking for the obtuse angle, sine 180 take away theta will give you that angle. Okay. So if B sine A is less than the size of A, which is less than the size of B, then two possible triangles exist. Okay, and you can see that existing in this diagram here, where you can see there's B and A, those sides. They are still all exactly the same size, and this angle A is the same here and here. It's just we don't know whether that angle B is acute or obtuse. Depends on the diagram. So, worked example. Correct the nearest degree. Find the angle U in a triangle given that t equals 7, u equals 12, and angle T is 25 degrees. So there's two possible triangles, one where U is acute and one where U is obtuse. Okay, so we can draw both. You can see my two triangles here. So in this first one, you can see I've gone for the obtuse, where T equals 7, U equals 12, and angle is 25 degrees. But we don't know if it looks like that one or if it looks like that one. So we can find both. Okay, so starting with my formula, my sine rule, subbing in my knowns and unknowns, I can get to sine u equals 0.724488, and then inverse sine gives you u equals 46.3 degrees, or u equals 133.57. So it's either case. Okay, we just don't know because the information that we were given could be either way. We just don't have enough information currently. This diagram's not drawn for us and we're not told anything about it. So because we were not told anything about it, we have to find it for both situations. We might get more information later. Now, an example where this was used, again, from a further maths exam, there's a bit of other work we're doing here, and then we're going to get to the ambiguous case. Let's go through it. So this is from the 2018 exam 2. So they do 2 exams in further maths. One's all multiple choice, one is all extended response. So Frank owns a tennis court. A diagram of his tennis court is shown below. Assume that all intersecting lines meet at right angles. Frank stands at point A. Another point on the court is labelled point B, and you can see the diagram there. What is the straight line distance in metres between point A and point B? Round your answer to 1 decimal place. Okay, well, looking at that, we've got point A, point B, and we've got a lovely right angled triangle there, don't we? Where I might just shorthand it here. So A, B, we want to find that X. That is 4.1. That distance is 2 logs of 6.4 plus 5.5. Let's bring out my CAS. 4 plus 5.5. So that's 18.3 meters. Okay, so what do we see there? We see a lovely right angled triangle with Pythagoras theorem that we can use. Okay, and I'm just going to solve this fairly swiftly. So square root of 4.1 squared plus 18.3 squared equal to, so 18.7537, and the rounding instruction was to 1 decimal place, so that's x equal to 18.8 meters. Okay, Frank hits a ball when it's at a height of 2.5 meters directly above point A. Assume the ball travels in a straight line to the ground at point B. What is the straight line distance in meters that the ball travels? Round your answer to the nearest whole number. Okay, so again, let's draw a little diagram of the situation. We have 2.1 meters, isn't that? 2.5. That's the height. There's point B, point A, and from A to B is 18.8. So I need to figure that out, because the ball travels from that height down to there. Okay, so again, x squared equals 2.5 squared plus 18.8 squared. So x equals square root 2.5 squared plus 18.8 squared. Enter. So 18.9655. So it travelled 19 meters. Okay. So that was a nice little recap of Pythagoras with some three-dimensional thinking in there. Let's look at the interesting part of this question that threw a lot of students. So Frank hits 2 balls from point A. For Frank's first hit, the ball strikes the ground at point P, 20.7 meters from point A. For Frank's second hit, the ball strikes the ground at point Q. Point Q is x meters from point A. Point Q is 10.4 meters from point P. The angle PAQ is 23.5 degrees. Okay. Now, there are 2 possible values for angle AQP. So let's think about that. They don't have where Q is here. So we have one possibility. It's very wonky. PAQ. That's 23.5. 20.7, and that's 10.4. We don't know that length there. Or it could have been sorry, I've drawn that very badly. PAQ. But again, with the same values, we don't know. We don't know what angle Q is. So, how can we find it? So, let's look at this acute case first, because once we know the acute, we can work out the obtuse. All right. So, working out my knowns and unknowns. So, I know 10.4 divided by sine 23.5 equal to 20.7 divided by sine Q. Okay, now just for ease of transposition, I'll flip that. So sine 23.5 divided by 10.4 equals sine Q divided by 20.7. So sine Q equals 20.7 times by sine 23.5 divided by 10.4. Now I'm taking up a fair amount of space here. In further maths, you probably wouldn't be doing all of this because you do more on your CAS. So I might just do this on my CAS now. So sine inverse sine 20.7 times by sine 23.5 degrees and 10.4, and I want to answer in decimal degrees, approximately equals. Okay, so Q equals 52.5292 degrees. So the first case, AQP, is going to be equal to 53 degrees. And second one is 180 degrees take away 53 degrees. So AQP equals 130. Let's just write that again. 127 degrees. Okay, so they were your two possible answers. Because the triangle was ambiguous, there were two possible answers. So if point Q is within the boundary of the chord, what is the value of X? Round your answer to the nearest meter. In other words, we want to make sure that Q lands somewhere in here. So length AQ has got to be less than 23.8 meters. Now it's more likely to be the obtuse angle. Why is that? Now let's work out both so we can see what we mean. Now how shall we do that? It's easier to use the cosine rule for that. Actually, I might just leave it there. You can delight yourself with that one.